Good morning, dear students. Today's lecture is about a new topic in the 8th chapter, Chemistry 1, and the topic is types of chemical reactions based on reaction velocity. There are different types of reactions in different cases. Like when it comes to thermochemistry, there are two reactions, endothermic, exothermic. Okay? There are many types of reactions when it comes to molecular nature of reaction, such as displacement, neutralization, etc., etc. But in chemical kinetics, our classification of reaction is based on their speeds, okay, their rates. And there are three possibilities. Some reactions will go at a very high speed, and we will call them fast reactions. Some reactions will go at a very, very slow speed, and we will call them slow reactions. And the third type will be those reactions which are neither fast nor slow, but they just follow a controlled environment where we can control their speeds. So, based on reaction velocities, there are three types of reactions. There are fast reactions, there are slow reactions, and there are moderate reactions. So, fast reactions. Now, the fast reactions are as fast as a microsecond. No watch or stopwatch or any setup in the laboratory can measure the time period of microsecond. So fast reactions, we cannot calculate their rates. Okay, so what kind of reactions are fast reactions? Ionic reactions. Ions are formed by the gain and loss of electrons, and when ions combine, the force of attraction is very fast, and electrons travel at a speed of light almost, if not equal to, but almost. So these reactions are very, very fast, and they complete instantaneously within a microsecond or even less than a microsecond. It could be nanosecond. So kindly see that those chemical reactions which complete instantly, almost in a very small time, in millisecond, microsecond, are known as the fast reactions. And in the laboratory, the ionic reactions are the fast reactions because they react at a very high rate. Because the ion exchange, the electron exchange is very quick. So all ionic reactions where they complete in a very short time, in a time period of less than a microsecond. So they are called as the fast reactions, and we cannot calculate their speed because there is no watch or stopwatch yet made for laboratory use which can do the job for us. So ionic reactions in the laboratory, very fast. They are redox reaction, oxidation reduction. Electrons are gained and they are lost. Electrons are very quick species, so obviously fast reactions. These are those reactions which are fast by nature and they are called fast reactions. Now, my dear friends, it is impossible to calculate their speed because I told you, right? HCl when meet with NaOH, their cations, anion, they quickly exchange. So quick that we can't even determine their speed. That takes place in a time period of less than a microsecond. That's why, my dear friend, we call them as the fast reactions. All right? You can see H and OH combine, the ions go towards the other ions. This is the other example. So just as fast reaction, there are also slow reactions. And slow reactions are those which take a lot of time. So fast reaction take about microseconds, but slow reaction take about years, sometimes centuries. Now, if a reaction will take place in 300 years, how can you calculate its speed? You have to live 300 years, which you can't. So slow reactions are also, we cannot find their rate. For example, we talk about slow reactions. So from months to centuries, okay, you can't find their rates anyway. So it's because they are very, very slow proceeding reactions. All right. So this is the second type of the reaction. So these are two types of reactions, slow and fast, and they are compared pretty nicely because the fasts are very fast reactions, and slow reactions are very, very slow reactions. So when we think about the fast reactions, we find that they take place in, let's say, millisecond, microsecond. And slow reaction, they take place in centuries, as I mentioned here. So let's check some examples. So carbon-13 is an isotope of carbon, and its half-life is 1783 years. The chemical reaction to convert carbon-13 to carbon-12, normal carbon, it will take about 1738 years. This is a very slow reaction. No human can actually find its rate. And diamond is made in the coal mines when coal is there for 300 years or more. Very slow reaction. Okay. Iron rusts, 6 months or later, depend upon the condition. So these are also very slow reaction, and their rate, we cannot determine their rates. Okay. Now the third type, which we are interested, is the moderate reaction. Neither fast nor slow, controllable in the laboratory. These are the reaction whose rate we can easily determine, and we can play with it. Like we can use these reactions in the industry, and if when we want, we can make them fast. When we want, we can make them slow. You can apply different factors to speed it up or slow it down. But that's only if the reaction has a rate which you can determine. So fast and slow rate we can't determine. So we cannot play with it. But the moderate reaction rate we can determine, so we can use the formulas to make the rate faster or slower and use the factors on them to make the rate faster or slower. Such reactions are mostly used by the industries so that the rates can be controlled. All right? Okay, we can determine their rates experimentally because they take minutes to hours. That's the fantastic option. Okay, the conditions are at the laboratory. We can change the condition. If it is happening in 4 minutes, we can make it go in 2 minutes. Like it will continually be a moderate reaction. Okay. Example, most covalent organic compounds are covalent compounds, and covalent species react moderately. If you remember this last reaction, acetic acid plus ethyl alcohol, ethyl acetate, if you remember those 5 flask experiment where we found the Kc, these are organic compounds. These are covalent bondings. Covalent bondings take time to be broken and then make new bondings. But that time is not too long. We'll also see that sucrose, sugar, table sugar, normal sugar, if it is added to water, it breaks down to glucose and fructose. So this is also a moderate reaction. So there are 3 types of reaction based on reaction velocity: slow, fast, and moderate. All right. So let's go for the question: why is that so? Why are some reactions slow and why are some reactions fast? What is the main controller behind the speed of the reactions? Okay, so the main controller is the concept of energy of activation. It is a concept of energy of activation which can make reaction slow or fast. All right. So what controls the speed of reaction is the concept of energy of activation. So why are some reactions slow, others fast? What is the controlling factor? And that's a very much important lecture for you if you are in class 11 or you're in class 12 or even if you're an improver. Energy of activation is a very good topic to learn and study. So let me explain to you more about it. Let's go line by line. So when do reactions start? When do they start? They start when you put the reactant A and reactant B in the same container. If A is in one container, B is in another container, the reaction will not start. So what happens when you mix the two reactants in one container? Their molecules are attracted towards each other. They go towards each other. They collide each other. When they collide each other, it produces energy, and mostly heat energy. This energy is called average internal energy of the reactants. This energy is different in different reactions, depending upon the nature of reactants and how much they are attracted to each other. Okay? Their bond energies, their molecular geometry, there are hundreds of factors which come into one name, nature of reactant. So sometimes two reactants don't like each other, so they collide slowly. They're very less average internal energies. All right. When two things collide, heat is produced. This is called average internal energy of the reactant, and we will use the term AIE. A for average, I for internal, and E for energies. So when the reactant molecules collide with each other, the heat is produced and we call it average internal energies. Sometimes the reactants are too much favorable for each other, they have good chemistry, they start to collide a lot and they produce a lot of energy. Sometimes they don't. So it depends upon different reactions and how reactants are compatible with each other physically and chemically. All right? Now you can see it entirely depends upon the nature of reactant, you know? Yeah, that's why various reactants produce different AIEs. So by AIEs, I mean average internal energies. Okay? Hope you understand that. Now these AIEs provide necessary energy as a heat. This energy will be used to break the old bonds and make the new bonds. And obviously, a chemical reaction is a name of the process. When the old bonds are broken and new bonds are formed, we call the process as a chemical reaction. So if AIEs are a lot, okay, and then it's favorable, the bonds can break easily. And if AIEs are less, the bond will not break easily. You can guess that the reaction with higher AIEs would be like faster ones, and very low AIEs will be really slower one. But it's not just the AIE completely controlling the reaction. Okay, the energy which the AIEs can be more or less, but still they are less the minimum energy required to convert all the reactants into products. Okay. So this energy is known as threshold energy. Now threshold means level below which they will not cross into products. Every chemical reaction is unique. Every chemical reaction requires a particular amount of energy below which the chemical reaction will not take place. This energy is called threshold energy. Now average internal energy provides some energy, but still they are not enough to equal threshold. For example, a chemical reaction requires 10 kilojoules energy and AIEs is 8 kilojoules. Now, how much left? 2. This 2 must be taken from outside. So when you open the gas in your kitchen, okay, methane gas, oxygen gas start colliding. They produce some AIEs, but those AIEs are less than the total energy required to break the old bonds. And there you go, you use a matchstick, or you have a sparker inside your stove, which provides that extra amount of energy to complete the reaction. So if AIE is more, you will require less outside energy to reach thresholds. If AIEs are less, you will require more outside energy to reach the threshold. So which energy is here without which we can't proceed the reaction? It is that third energy, that missing energy between the internal energies and the threshold energy. That energy is known as energy of activation. Okay? Here we go. Average internal energy provides some part of the threshold energy, but still there's some energy remaining. It must come from outside. Okay? And this additional amount of energy is required to complete the reactions or to completely convert the reactant into products is known as energy of activation or activation energy or EA. So if a reaction has a large EA, it will take a lot of time because absorbing energy takes time. Absorbing heat is a slow process. So if a chemical reaction has a very high value of EA, all right, it means it is getting very less amount of energy from the internal energy and remaining mostly coming from outside. For example, there are two reactions, A and B. A reaction has 10 threshold, B also has 10 threshold. Now, A reactant has 2 joule average internal energy. So 8 is required. And B has 9 activation in average internal energy. So 1 is required. You can tell me which will occur faster. Yes, 1. Because absorbing energy takes time. So here we go. That is, yeah. Threshold energy is equal to average internal energy plus energy of activation. So a reaction is completely controlled by the energy of activation. And of course, when you minus average internal energy from the threshold energy, the remaining amount is known as the energy of activation. We attempt the fourth example in the book, and it is on page number, I'm not sure, 233, where the question says that threshold energy is 31 kilojoule per mole, average internal energy is 12 kilojoule per mole. How much energy of activation required? So 31 minus 21, and that is 19 kilojoule, the energy of activation. Very simple problems. I hope you understand those, right? Now with the help of graph, I will try to make you understand this. All right, I will use this. I will use some tools here. Okay. Now this is 0. Everyone look at the screen. This where the two purple lines collide, this is 0. This is origin. And y-axis shows the energy. Okay. From this point, are you all looking at the screen, at the graph? From this point to this point. This is the amount of energy that reactants are providing. It's called average internal energy or AIE. Let's say this is 5, 10, 10, 20, 30, 40, 50, 60. The threshold is 60 and 20 is provided by the reactants. How much remaining? 40. This 40 is known as energy of activation. From this black line to this black line, this is the energy of activation. From this black line to this purple x-axis, the internal energy of the reactants. And from purple line to the threshold, this is the total energy required. So this reaction, guys, can you tell me will it be a slow or fast reaction? Slow reaction. Why? Because see, the average internal energy is less, 20, and 40 is the energy of activation to make it 60. It's a slow reaction. So what happens? What does this graph indicate? The graph indicates that when the reactants collide, the collision that they must get to as hot, their energy must go to this peak. Why? Because the kind of bonding they have, they will only break when they will reach here. The point where you can see this red dot is called activated complex. Reactants are bonded, the bonds are trying to break, and making and breaking is happening, and that's where when the energy of these bonds reach this level, it is where the cleavage takes place. The old bonds collapse, and the energy lowers. See, the graph is going down, right? And did you observe something, my dear fellows? The reactant's energy was 20. See that? It's 20. But the product size is only 10. It means the reactant began with 10 kilojoule per mole and the product with 20. Sorry, 20 for the reactants and 10. It means that 10 will be released out. This is an exothermic reaction. Guys, if this green line and this green line, if they are like this, if products have lesser internal energy, it means this energy is surplus, extra out. If this green line was here, then this will be coming from outside. It will be an endothermic reaction. I'll explain that for you, but first look here. Do you see? That is called the activated complex. Energy barrier, because the reactants got to this place. ER for energy of reactants. Okay. EA for energy of activation, and ET for threshold energy. So ER was available from collisions. EA came from outside as heat to reach the energy ET, because ET is enough energy to destroy the activated complex. Reactants have bonded, but they don't know what to do. They are confused unless a motor comes on them and energy goes like ET and the bonds break and they collapse. But look at the final stage. The products have internal energies lower than the reactants. So this is the difference of energy which must be released. This is delta E negative. This is an exothermic reaction. Let me explain to you in the next slide. Velocity of reaction depends on the relative energy of activation. If a high activation, absorption will be slow reaction. And small energy activation, fast reaction. Okay? Fast reaction have EA very slow, and slow reaction have EA very large. Now this graph, what I want you to focus: exothermic, endothermic. The graph is explaining that AB's energy is this much and CD is this much. So this much energy is extra, must be expelled out. AB's energy is this much and CD is higher than them. This must come from outside. So this energy diagram explains why some are slow reactions, some are fast reactions, why some are endo and some are exo. Do make it kindly and enjoy doing the fourth example. And by example, I remind of a question by Sarah Bibi, and she asked me about the third example. So I solved the third example for you guys. Maybe many other students would face difficulty. The third example was this reaction. C2H2 is ethine, C2H6 is ethane. Let me explain it for you. Right? Now, ethine, if you know hybridization, sp hybridization, ethine is HC triple bond CH. So that in a triple bond, there is a sigma bond in the middle and two bonds are pi. So when a pi bond opens, if you remember, a pi bond is a panel over there. If energy is given, pi bond opens, one atom can bond here, one atom can bond here. There are two pi bonds. So H here on the top, and then H down. So there are four atoms of hydrogen will attack on ethine to make CH3. Don't go into these molecular geometries, but if you have learned hybridization, then you know that these pi bonds, basically the first pi bond will break, one H will come on this carbon, one H will come on this carbon, it will be H2C. Then if two H come from downside, then CH3. Now this is a very simple: 1 mole ethine, 2 mole of hydrogen, 1 mole of ethane. So if ethane's rate of appearance is 5, ethyne's will be 5 because 1 1. For ethyne, it will be disappearance as a reactant. If 5 is ethane's appearance, so 10 will be hydrogen's disappearance because there are 2 moles of hydrogen for each mole of ethane. Look at this. If the ethane is appearing produced at 0.25 mole per dm cube speed, since 1 mole of ethyne is required to make 1 mole of ethane, so the rate of appearance of ethane will be same as the rate of disappearance of ethyne. So 0.25 mole per dm cube is same. Wait a minute. If they were, look at this, 1 C2H2. If there were 3 C2H2, then you would multiply this 0.25 with 3. If there were, like next is the 2H2. So what happens? To produce 1 mole C2H6, 2 moles of H2 are required. So the rate of this, so the H2 will be consumed at double speed. So if 0.25 is the rate for the ethane, just to multiply 0.50. Suppose if it was 3H2, it will be into 3, 0.75. Common sense? Thank you so much. It was common sense question. You guys are preparing for your test on Wednesday. I hope when you receive this video, most of the students must have received their testing codes. Okay. In the testing codes, you don't have to give your email address, just our code, name, father's name, and a username. A username should be your name and 001. For next test, it will be your name 002. Password can be anything your own and unique. Okay. So the test will be available at 8 p.m. tomorrow. Kindly be present and be logged in. If anyone does not receive the code, please text me. Don't worry, just text me. Okay, I didn't find the code. This is my email, didn't find the code. But wait until 8 p.m. today because we are still in the process of sending the codes. It's a long process, you know. So once we finish sending all the codes, we will leave a message in WhatsApp that all the students are sent the code. If anyone wants the code now, then response. So as per response, we will send the codes to everyone. I hope everyone will get the codes and we'll have a good test on Wednesday, which is tomorrow. Tomorrow's class will be factors affecting the rate. It'll be last topic, and by Thursday we'll finish it. So by Thursday, our 8th chapter will also be complete. All right. So thank you so much. I hope that you know about the entrance test preparation online classes and testing from 1st June. In case if that happens, I will highly encourage first year students to take part in the same as well. That will be your revision from first chapter to 8th chapter in chemistry, also in physics. So stay home, stay safe, study and progress. Goodbye.